Okay, here is problem 86, page 658. I have assigned you problem 87. Okay, and you'll find if you look at the last problems associated with parabolas, last problems associated with ellipses, last problems associated with hyperbola, and they're always, they might even have the same numbers. They might all be 86, 87. They're certainly in the late 80s in all cases. They're all very similar looking, and what they're dealing with is something called the conic quadratic. And they're kind of building up, they're taking baby steps towards the conic quadratic. If you want to see what that is, I've actually got some extra material that's appended to the Canvas section for this week called the conic quadratic. What the conic quadratic is, it says if you've got a quadratic equation in both x and y, and it's always written like this, okay? I think that stayed on the screen, where a, b, c, d, e, f are all constants, and then x and y are the two variables. This form produces a conic section, depending on what a, b, c, d, e, and f are. And you can tell from this form by various features of these a, b, c's, d, e, and f, which conic you're dealing with. You might remember previously I said, oh, you got to look at the sign between a and y, x squared and y squared, which is effectively the values of a and c. And if it's positive, you're probably dealing with a quadratic. So it's a little bit more complex than that. And this problem we're dealing with, let me just read what it says. It says, show the form ax squared plus cy squared plus f. So they've said, let's let b be equal to 0, let d and e be equal to 0. You're dealing with ax squared plus cy squared plus f, where a, c, and f are not 0. It gets pretty non-interesting if everybody's 0. But it says, show that this form, when a and c have the same sign, either they're both positive or they're both negative, doesn't matter, but whatever they are, that sign is different from that on f. So if they're both positive, f is negative. If they're both negative, f is positive. And show that what you get is the equation of an ellipse centered on the origin, provided a and c are different, or a circle centered on the origin, provided a and c are the same. Okay, maybe that's all I'm going to say right now about this. We will talk about this within the next week or so. So just very quickly, let's just take this form that they gave us with all of these constraints on a, c, and f. Let me divide everybody through by f. Okay, so I'm going to write that x squared all over f over a plus, where am I? Y squared f over c plus 1, yikes, plus 1 is equal to 0. So I'm going to write that right over here, and I'm going to write it like this, x all over minus f over a plus y squared minus f over c is equal to 1. So that looks a lot like an ellipse, right? It's got this funny term f over a. So minus f over a. So remember what this caveat up here said. It said a and c have the same sign, f is different. So if a is negative, f is positive. That means the quantity minus f over a is positive. Great. Let's call it I don't know what I want to call it. I kind of want to call it a squared. I'm going to call it a squared. It's positive, so I can call it a squared. Likewise, a and c have the same sign. F is different, so if c is a and c are positive, f is negative, minus a negative number or positive number. If a and c are negative, f is positive, minus f over negative number positive. So I'm going to call minus f over c a positive number equal to b squared. And when I put that in, then I get x squared all over a squared plus y squared all over b squared is equal to 1. Okay, and provided a does not equal b, which is to say this capital A is not equal to capital C, then this is an ellipse. And if this is an ellipse, and if a equals b, then I can rewrite this as I'm going to call them both r. Then in that case I can write this one more time. Always down at the bottom, I could write it x squared plus y squared equals r squared, and that's a circle. So that's the type of machinations that get involved with this conic quadratic. And that's what the author expected of you for problem 86.